Oh, great, you got
Do you
them.
have a place you want them?
Oh yeah, let's just set them over here.
Cool. I don't see the spare parts.
Yeah, William says he has them back in his car. He'll bring them when he comes later.
Okay.
Okay, would one of you guys mind just adjusting this to make sure that everything is in the frame? So I'm going to record the talk here. So you just, I guess, loosen this, and then you can tilt it. Just make sure everything is, you can see everything if I'm pointing to something or it's not out of the frame. And I think it's recording now. Okay. Yep. Thanks. Okay, so right, so everyone gather around. Are you able to see the screen? So, all right, would you mind turning off the fume extractor for at least the next few minutes? Okay, thanks. All right, so welcome back everyone who was here last week, and welcome everyone here who's new this week. So last week I gave a brief intro to amateur radio and the propagation in the ionosphere, which is how these radios are going to be able to communicate over long distances. So this week I'm going to give a short overview of the circuit itself and how the circuit works. So you'll know a little bit more about what all the components are doing in the circuit that you're putting together. And so let me begin just by showing the block diagram. So this block diagram I got from the manual of the radio, and this and the manual, if you read it, it actually goes into a great amount of detail about all of these different components of the circuit. And you can probably spend about an hour just talking about each one of them. So I'm not going to go into that much detail. I'm just going to give a overview of high-level overview of what's going on. So the first thing I highlighted here is this red path, which is what happens when the radio is transmitting. So I'll first talk about what happens when you transmit, and then we'll talk about what happens when you receive, because it's able to do both of these. So this transmit path has multiple components. So it has an RF signal generator, then it has a power amplifier, and then it goes through this transmit-receive switch, and then something called a low-pass filter, and then to the antenna. So we'll start with where the signal comes from, which is this RF signal source. So the circuit uses a special integrated circuit that is called the SI5351. And this is a very widely used and versatile chip. So it has a lot of very complicated stuff inside of it. And basically you can think of it as a square wave generator that you can program to generate square waves of almost arbitrary frequencies. So the way it does that is it needs some sort of reference to give it a reference of time, which is this input right here. So it takes in a 25 megahertz signal, and that's its standard that it uses to generate all other frequencies. So if this frequency here is inaccurate, all the output frequencies will be inaccurate, because inside this chip, all it's doing is multiplying and dividing that frequency by integers in order to generate some output frequency. So this input frequency is generated by this special chip, and this is a picture of what it looks like on your board. If you look on the bottom of your board, you'll see this little rectangular silver chip right here, and that's called a temperature compensated crystal oscillator. So it has a little piece of quartz inside of it, which is cut to a certain size, so it vibrates at just the right frequency to produce this 25 megahertz signal. And it has this additional feature, which it's temperature compensated. And the advantage of that is the quartz, as it heats up or cools down, it changes its properties and size slightly. And because it's just a mechanical oscillator, that would get it out of tune. So there is inside of here some circuitry that measures the ambient temperature and can compensate for that. So it can maybe add or subtract some capacitance to retune the system in order to make sure that this frequency stays very stable. And you need this to be very stable because when you're transmitting and receiving these frequencies, remember this radio is a frequency shift keying radio, so the data is encoded in the frequency of your signal. So if that frequency is off or is drifting, it's going to mess up your digital signal that you're trying to encode. So, so that generates the reference frequency, and then this chip multiplies and divides that frequency by certain integer multiples, and then generates 3 square wave outputs. And you can program it to generate pretty much whatever frequencies you want. And that's done through this interface right here, which hooks up to the microcontroller chip that has all the code that your radio is running. So, so once you have those frequencies, you can use that to generate the frequency that you want to transmit on the radio. So this chip, it can generate any frequency from 3.5 kilohertz up to 200 megahertz. So it's a very, that covers a very wide range of frequencies. So in our case, we want to generate frequencies between 3 megahertz and 30 megahertz. So this chip is easily able to do that. So you just program the chip to generate the frequency you want, and you'll get 2 square waves coming out of the output there. And notice the way that I drew them, one square wave is high while the other one is low. And it turns out that that's very important because of the next stage of where those square waves go. So in order to generate a powerful radio signal that goes out onto the air, you need to amplify those square waves because those are just very low voltage square waves coming out of that chip. So they go through these chips, which are AND gates, which buffer the signal a little bit and boost the power, but not by very much. And then those go into the gates of these MOSFETs right here. So if you got to that step in the construction where you had to solder those 4 transistors, so raise your hand if you've gotten to that step so far. So these are the 4 transistors that you're soldering. They look like this, and they have that washer that presses down on them. And the reason is that for that washer is for heat sinking, because this is what's generating all the power for the radio. So there's a large amount of voltage and current on those transistors, so they get hot. And so that's why they need to have that heat sink. So notice in the circuit, these 2 are in parallel. So they are, the same points are connected together on both of these transistors. So that just, so they're both actually doing the same thing. These 2 here and these 2 here. So does anyone know why you would connect them in parallel like that? What would be a reason for?
To handle additional current?
Yes, exactly. So you can handle more current. So each one only has to handle half of the current. So this is a simple way to get more power out of the radio than you could if you just used single transistors by themselves. So so now these transistors, they're being driven by square waves. And the square wave is large enough that it'll be about, I think at this point it's probably about 5 volts, either 3.3 or 5 volt square wave that's driving these transistors. And so who knows about the transistors, the MOSFET transistors, what will happen when you put this square wave? Well, actually, let me back up a bit. Raise your hand if you're not familiar with MOSFET transistors, or if you have not heard of them before. Okay, so we have one person. So, okay, so a few people are not entirely familiar with these. So, so let me explain a little bit of what these different connections are. So one of these connections goes to ground, and this is called the source of the MOSFET. The other one here is called the drain, and then this one is called the gate. So the MOSFET is a special kind of doped silicon structure that has which is represented by these bars right here. And on top of it, it has an insulating layer and then a metallic electrode. So the gate is that it's connected inside the transistor to this metallic electrode, and it's completely insulated. So so there can be charge buildup here, but you can't pass a DC current through that port. So so when you apply a voltage here, all it'll do is it'll charge up that electrode or discharge it. And as soon as it's charged, then the current will stop flowing. And the name of this transistor, MOSFET, it stands for metal oxide semiconductor field effect transistor. So field effect means that the field of this charge penetrates into the silicon, and it actually, I won't go into the physics of it, but it can actually cause this to become conducting or non-conducting. So when you apply a charge to the gate, it'll cause the silicon to conduct. When you remove the charge, it stops conducting. So basically, it's like a switch. So, and it's a switch you can turn on and off very rapidly just by applying a voltage here. So, so what both of these transistors are acting like are switches. And there are two switches in parallel, so you can double the amount of current they can pass. And they're just turning on and off. And and now remember I said that there's two square waves, and one of them is high while the other one is low. So that means that on one side the switches are on, while on the other side these are off, and then vice versa for the other half of the cycle. So they're constantly switching back and forth. So those switches are connected to the two sides of this transformer. So do you guys remember, so who's made this part so far? Raise your hand if you've wound this transformer. So you remember you had to wind 1.5 turns, and then you had a center tap, and then another 1.5 turns. That was this right here. So this is the center tap, and then you had 1.5 turns here, and then 1.5 turns there, and those two sides are connected to those two switches. And then the center tap goes through this inductor up to 12 volts. And then you wound 2 turns for the secondary of the transformer, and that's this right here. So, this circuit actually has, it works in a rather interesting way because it's constantly switching back and forth between this side being on and this side being on. And you have a current that's flowing through this inductor here, which flows into the center tap. And now what's going to happen to that current when it comes out, when you keep switching these transistors back and forth?
Between up and down?
Yeah, it'll reverse the direction of that current. So during one half of the cycle, this current will flow upwards through this half, like that. And then during the other half of the cycle, it'll flow downwards through that half there. So you keep reversing that current back and forth on the primary of the transformer. But there's a property of inductors that would tend to oppose that changing current. So does anyone know what happens in inductors when you try to change the current very rapidly?
You get a back EMF.
Yeah, so you get something called a back EMF, where there's a induced voltage that tries to oppose that change in current. And so you can think of inductors as things that always try to oppose a change in current. Or more precisely, there's something that tries to oppose a change in the magnetic flux or magnetic field that goes through the core of the inductor. But this core has multiple windings on it. It has the primary windings and the secondary windings. And the only thing that it tries to oppose is a change in the total current of all of these, or in other words, the total magnetic flux going through that core. So if you reverse a current here, the core will induce a electric field that'll change currents elsewhere to try to make sure that this flux is constant. So what will happen to the current on the other side? I'll let you guys think about it for a bit. So remember how you wound those things. You had some primary windings going around multiple times around this core. And when you pass a current through there, it'll cause magnetic flux to go upwards through the core. So it'll come upwards here through the middle, and then the magnetic field will wrap around through the two sides of this core and return coming up the bottom. So this transformer will try to keep that same magnetic flux. So and that magnetic flux starts out being generated by the current going around the primary side. So if that's pointing upwards, then you'll have flux going upwards. And now if you suddenly turn this off and turn the other side on, that'll immediately reverse. So the primary side is now suddenly creating magnetic flux pointing the opposite way. So the inductor will try to keep that magnetic flux constant, prevent it from changing. So what's going to have to happen to the current on the secondary, which is also wound around that same core?
Does it change in the opposite direction?
Yeah, so you'll have to have a sudden change in the current over here so that the sum of the flux generated by this side and that side remains the same. So the fluxes will add together. So if this one suddenly reverses direction, this one you'll have to have a current over here that also suddenly reverses direction, so that when you add the two together, the flux stays constant. So, so what that means is on the output here, you get a square wave of current. So it'll have a current that flows out in one direction here, and then when this switches, it'll instantaneously change the current direction in the primary, which will cause this to have to flip to cancel that change, and then you'll reverse the direction of the current here. So you have a current that'll flow this way for one half of the cycle, and then that way for the other half of the cycle. So, and that current can be much bigger than any of the currents on the input here. So these could be very weak signals coming in here, and indeed they are. And on the output, you get this very, very strong current. So this could be like maybe half an amp or so of current flowing back and forth right here. So, so now you have this very powerful signal, and that can output a large amount of power, which you can then use to radiate and make a signal that could be heard very far away. So, but there's another thing that you need between this and your antenna. So can anyone tell me what you need? So why can't you just hook this right up to your antenna?
Square wave filter.
A filter. So why do you need a filter?
You don't want to send a square wave.
So why do you not want to send a square wave?
That's a good answer. It has like a very wide spectrum, right? They cannot noise.
So yeah, so the reason why you don't want to send a square wave is because of the way this radio works. Remember, it's frequency shift keying, so you want to transmit a frequency, and you encode the data in that frequency. The problem with the square wave is that it's not just one frequency, it's composed of many frequencies. So this shows something called a Fourier series. So raise your hand if you're not familiar with Fourier series. So, okay, so everyone's heard of that before. So, so you can make a square wave by summing together a bunch of sine waves of many different frequencies. And that means if you were to transmit a square wave into your antenna, well, first of all, the antenna might not behave the same at all those different frequencies. So the signal coming out is probably not going to be a square wave, but it will be some weird wave, and that wave will contain all of these different frequencies. So in the case of a square wave, it's composed of odd harmonics, so odd integer multiples of the fundamental frequency. So whatever the frequency of the square wave is, it'll have a sine wave component at that frequency, and then all the odd multiples of that. And this comes from the manual. You can look this up here. The guy who designed the circuit measured what that square wave frequency spectrum looked like with, this was with a 3.5 megahertz square wave. And you can see this here is the 3.5 megahertz. So you see a very strong peak. So this is, the x-axis is frequency, and then the y-axis is the signal strength. So you see a very strong peak at 3.5 megahertz, and then this is twice the frequency. There's just a little bit of signal there, mainly coming from some asymmetry between the high part and the low part of the square wave. If there aren't exactly equal time duration, you can get a little bit of the second harmonic, but mainly it's the odd harmonics that you see. So, so when you transmit, so if you were to hook that up to your antenna and transmit, you would be transmitting on your intended frequency, but you'd also have signals on all these other frequencies too, which then could be causing unwanted interference. And that's, people would not be very happy if you were to do something like that. If it, especially if it lands outside of the amateur radio bands, you could be in violation of the law. So, so you need to make sure that these things are filtered out before they get out to your antenna. So, so what sort of filter would you use to eliminate those other frequencies?
Low pass?
Yes, a low-pass filter. So a low-pass filter will pass frequencies below a certain limit and then block frequencies above that limit. So if you choose your low-pass filter cutoff to be above your fundamental frequency, but below all those other frequencies, then you'll just be left with that fundamental frequency. So this is an example. I took this from one of the pages of the manual. This is the schematic for the 80 meter low-pass filter. So this input here represents the square wave coming from that power amplifier, and then it goes through these combinations of inductors and capacitors. So the capacitors tend to look like a short at higher frequencies. So it'll tend to short your RF to ground at high frequencies, but it looks open at low frequencies. So the low frequency can pass. And then the inductor, it tends to look like an open circuit at high frequency, so it'll tend to block your high frequency, but it looks like a short at low frequency, so the low frequency will pass. So that's roughly what's happening in those filters. The low frequencies are able to go through, and then the high frequencies just get reflected back and stay in that square wave in the power amplifier. And this is what it looks like on your boards. When you're winding all these small toroids, if you've gotten to that step yet, that's what you're winding. You're winding these inductors in that filter, and these capacitors here are these ones you're putting in right next to them. So now this plot I also got from the manual. So this shows what's called the transfer function of that filter. So this tells you how strong of an output signal you get for a given input signal as a function of frequency. So this plot starts at 1 megahertz and goes all the way up to 21 megahertz. And the blue one, that's something different. So the thing we're interested in is the red curve here. So you see it starts out at the top here, and then it goes down. So your signal strength drops as you go up in frequency, and then it stays pretty low. So the scale that is being used to measure that signal strength is something called dB. So raise your hand if you have not heard about dB before. Okay, so everybody is familiar with dB. So it goes from 0 dB, which in terms of a ratio of input to output signal, what does 0 dB mean?
Like it equals to one another, the ratio is 1.
So the ratio is 1, yes. So dB, because it's a logarithmic scale, a dB of 0 means it's a ratio of 1. So it's 10 raised to the 0th power. And now this trace here, or this level here says minus 10. So what does minus 10 dB mean? So how much, so if you input a signal with 1 watt, and the output signal is reduced by 10 dB, or minus 10 dB relative to the input, then what is the power of the output signal?
0.1?
0.1 watts, yeah, so it's a factor of 10. And then what about 20 dB? Is that a factor of 20? So what would 20 dB then? If you have 1 watt in, and then 20 dB reduction, then the output power is what?
10 milliwatts.
Yeah, so it's a hundredth of a watt. So this is 10 to the minus 2, 10 to the minus 1. So 30 dBs, 10 to the minus 3, and so on. So you could see, because this is a logarithmic scale, this curve represents a very rapid drop-off in power. So this is designed to pass 3.5 megahertz, which is right here. So that's very close to 0 dB. So almost all of your power goes out. And then by the time you get up to the, so the second harmonic is 7 megahertz right here. So it's already minus 26 dB. So that's, your power is reduced by a factor of 100, more than 100. And remember, the second harmonic in that power spectrum started out pretty low to begin with. So this was the second harmonic here. So it's already pretty low. Now it's been reduced by another factor of 100. So that's pretty good. And then the next one is the third harmonic. So the third harmonic will be at 10.5 megahertz, which is right around here. So you see that's minus 67 dB. So that one is going to be extremely low power. So this is a very good filter. So it's going to make sure you're not causing interference to anybody else. So So this is if you wanted to transmit on 3.5 megahertz. So does anybody remember what band that was? So people who were here last week, I talked about all the different amateur radio bands. So they had different frequency limits, upper and lower frequency limits. So which one was the 3.5 megahertz? So I remember they're all designated by a certain number of meters. So people call them, so there's like a 20 meter band, 40 meter band, 80 meter band, 160 meter band, and that's sort of a round number of meters that's close to the wavelength of those waves. So what sort of wavelength is 3.5 megahertz?
80?
Yep.
80, yes, 80 meters. So this is for the 80 meter band. So suppose you wanted to transmit on the 40 meter band, what frequency would you use?
7 megahertz.
7 megahertz, yeah. So if you use this filter, what's going to happen?
You're not transmitting a lot of power.
Yeah, so if you just change the frequency, which remember that chip, you could just program it to output whatever frequency you want. You just change it to 7 megahertz. Now all of a sudden your signal is going to be reduced by over 100 times. So that's a problem if you want to be able to transmit on multiple bands with this radio. So how would you fix something like that? How can you transmit on multiple bands while still preventing these harmonics from being radiated?
More filters.
Yes, more filters. So that's why this radio actually has multiple filters. So the circuit will switch in different filters based on what frequency you're trying to transmit. So if you're transmitting these low frequencies, it'll use the 80 meter low pass filter, and so it'll filter out all those harmonics. Once you go up to a higher frequency band, like the 40 meter band, your fundamental frequency will be higher, all your harmonics will be higher. So the circuit will switch, turn this one off and switch to the 40 meter filter, which has a higher cutoff frequency. So it'll pass your 7 megahertz signal and then block the integer multiples of that. And then if you tune to even higher frequencies, then it'll switch to this one. This is the 30 meter band and 20 meter band filter. And those are close enough in frequency, you could actually use the same filter for both of them. So you can block harmonics of both 20 and 30 meter bands at the same time with the same filter. So that's if you're using the 80 to 20 meter band version. If you're using the 20 to 10 meter band version, then that's why you need the different components for these filters, because you need to filter out different harmonics and different frequencies. So, we actually got those components today. So if you're waiting to build that filter, we have those for you to build it today. So,
Hey, Rob,
yeah.
in between the two options for the radios, is the 20 meter filter actually the components differently?
So yeah, it is slightly different, because I think this one was designed to pass the 30 meter band as well.
Yeah. Why can't the 20 to 10 meter option also pass 30?
Because I think I think it's designed, so unfortunately the data sheet or this manual only goes into detail about the low band filters, so it doesn't talk about the choice of components and stuff for the high band, but I'm guessing it probably allows like this one can do both the 30 and 20 meter band, probably on the high band one, maybe it can do both 20 and 15 or something like that, so it shifts the frequency up a little bit higher. But I haven't looked into the details of what exactly the cutoff frequencies are, but I suspect it's something like that.
But between the two options for radios, it's the components of these filters that are the difference.
Yeah, so that's the difference. There's one other difference, which is the radio firmware needs to know which of these filters to switch in based on which frequency you want to transmit. So there's a jumper wire where you short two pins together, and then the microcontroller reads in that voltage between those two pins, and if it's shorted, it knows that you're telling it to do the high band version. And so when you program it to transmit on one of these higher frequencies, it'll know which of these filters to switch in, and it'll know that it's the higher band version of the filters, not the low band version, because otherwise it doesn't have any way of knowing what components you put into your circuit. All right, yeah, thanks, good questions. Any other questions about that? So So if you need to switch these filters, you need some sort of switches here to connect to your, so here's your antenna, and here's that power amplifier. So you need to open the switches of the close the switches of the filter that you are using on both sides so that your signal can then pass through like that and gets blocked from going through these other filters. So, so what do you think we should use as a switch here? There's actually a lot of different options, and actually, if you look at different radio circuits, people use many different things for these sorts of switches. But what are some examples of things that you could use as a switch?
Transistor.
So you could use a transistor. That's one option. So like I was talking about those MOSFETs acting as switches. So that's something that you could use. In some cases, though, it's hard to get those to work at these higher power levels. So if you want to have it act as a switch to just pass a signal from one side to another, because you can have a high voltage on this side and on this side. Usually the MOSFETs prefer one side to be grounded. So that makes it a little bit difficult to use a transistor there, but there's still some ways to do that.
Mechanical relay.
A relay, yeah. So does anyone not know what a relay is, or have you not heard of a relay before? So, so a relay is sort of like a mechanical switch, just like a light switch, except that instead of actuating it with your finger, it has an electromagnet. So you apply current, and then it'll pull the switch over one way or the other based on whether the current's on or off. So it's, and you could also do this with a manual switch too. You could just have a manual switch and have multiple positions, and it would be a bit of a pain because then you have to, whenever you want to change bands, you'd have to switch it. But the nice thing of having an electrically controlled switch is the microcontroller can do all that for you, and you don't have to manually change it. So, so a lot of radios do actually use relays, and so they'll just have these mechanical switches with electromagnets to switch these things on and off, and you'll hear them clicking when they do that. So this circuit actually uses something different from all those, and I don't know if people have heard of it before, but it is something that is not too common, but it is actually used in a lot of radio circuits. It's something called a pin diode. So it turns out you can use a diode as a switch. And this is a very, it's sort of not the way that people normally think about diodes. You normally think of diodes as a sort of component that lets current pass in one direction and blocks it from passing the other direction. But actually this, and a switch is different from that because the switch lets current flow in both directions when it's on and blocks it in both directions when it's off. So normally you'd think, oh, this is very different functionality. You can't use a diode as a switch. But it turns out that there's a clever way you can do that, and it has to do with some of the properties of the diodes when you go up to very high frequency and when you reverse the current at very high frequencies. So when so this is a diagram that shows what's going on inside of the standard semiconductor diode. So you have silicon that has these different materials that are called dopants added to it. And on one side, these dopants have very loosely bound electrons. So at room temperature, those electrons are able to pop off and move around inside the silicon. And on the other side, you have things that suck in electrons and leave basically an orbital around one of the silicon atoms that's missing an electron. And actually, the way that the holes behave is almost exactly the same as electrons. If an electron hops to fill that hole, it leaves a hole in the next atom, which is the same as if it was a positive thing that was moving through the crystal. So, so you have these holes that can move around over here, and these electrons that can move around over here. And I won't go into the detail. We could talk about that later. You can look that up. But the way that they interact in the middle is that the holes and the electrons tend to annihilate each other. So the electrons tend to fill in the holes and cause them to disappear. And that creates this, it causes them to diffuse and recombine in a way that imbalances the charge on each side and creates this voltage difference across the diode. And then it comes to equilibrium and this process stops. And the thing that makes it behave like a one-way valve is when you change this voltage, if you try to eliminate that voltage that's keeping the electrons and holes separate, then they'll tend to recombine again. And that's how you get this current. And then if you increase that voltage, then they'll stay even more separate, and you get no current. So that's what's going on normally. But the difference is when you try to reduce that voltage and that allow the electrons in the holes to diffuse past each other and recombine, and you suddenly reverse it, those holes and electrons need a little bit of time to move back into their respective regions. And so if that the current is reversing fast enough, they actually don't have enough time to separate, and you'll have this charge continually present in the middle that's still able to flow back and forth. So if you put a high enough frequency into a diode, it'll actually never turn off. It just doesn't have enough time to turn off when the current direction reverses. And you can actually increase that amount of time by adding this extra region in the middle between the P and N-type doped silicon called intrinsic, or I. So that has no doping at all. And so that increases this region in which the electrons and holes are commingling and recombining. And it takes longer to clear out that region when you reverse it. And the other advantage of that is when you do reverse it and pull all these back into their respective regions, you have this big empty region of intrinsic silicon which has very little charge in it. And if you have free charge here and free charges here and no free charge there, what does that look like? What sort of electrical component has something with movable charge here, and no charge between them?
Capacitor.
A capacitor, yeah. And what happens if you increase the distance between the two electrodes of the capacitor? What does that do to its capacitance? Does it go up or down? I heard someone say something? Down. So yes, so when you separate the electrodes of a capacitor, it reduces its capacitance. So the bigger this region is, the more the lower the capacitance, which actually reduces the amount of electrical coupling between the two sides. So it isolates them more. So if you had an RF signal on one side and you applied a DC voltage across this diode to separate the charge, then it looks like a very tiny capacitor. So it tends to block that RF signal from getting to the other side. If you were to forward bias it so the charges can then enter in this region and commingle, and then if you have a very high frequency RF signal, they'll just sort of shake back and forth in the middle and never completely clear out, and they'll actually be able to pass that RF signal from one side to the other. So people actually make diodes with this sort of construction in order to behave like a switch. So they actually, because normally you want your diode, if you're using it to rectify a signal and act like a one-way valve, you don't want that effect, but you can actually design it to increase that effect if that's what you intend. So they call these pin diodes for positive, intrinsic, negative, or P, positive doping, intrinsic, negative doping. And but it turns out that there are some common diodes that people use for rectification, like this one. It's the 1N4007. It's designed to withstand up to 1,000 volts and of reverse voltage without breaking. And because of that, they actually have, I believe they have some sort of internal construction that's similar enough to this that you can actually use it as a pin diode, even though it's not intended for that purpose. But it's an extremely common and cheap part. So that's actually what is in your kit, and it uses these pin diodes as switches. And so the conclusion here is the way that you turn it on is you apply a forward current through the diode, which fills this region with the mobile charges. And then to turn it off, you apply reverse voltage, so you get no current, and it acts like a capacitor, that very tiny capacitor, and blocks the RF. So any questions about that? So this is the circuit diagram from the manual of these three different filters. So here's 1, 2, 3 of these filters, and you see the inductors and capacitors there. And on the input and output of each of these, you see there's a pair of diodes. So those diodes have a DC current path. So if you look here, there's a positive supply voltage that goes through an inductor, and then through the diode, and then through another inductor, and through another inductor, and then to a MOSFET. So this MOSFET is behaving like a switch, and one end is grounded, like I say you typically try to do with this MOSFET. And when this MOSFET is turned on, then then you'll have a current that flows from your supply through that diode and through those inductors to ground. So that will have a current flowing through that diode, which will then make it behave like a switch that's turned on. And also you have another path here going through the second diode through the same MOSFET to ground. So that way, these two sides of the diodes, neither one of them is connected to ground, so that you'll have a very high voltage oscillating there. But it still behaves like a switch, just like this MOSFET, where one side usually has to be grounded. So, so when that MOSFET is on, then your signal from your power amplifier will come in along this path, and these diodes will act like turned on switches, and will pass through the filter and go out to your antenna. And then these diodes here, if this MOSFET is turned off, they can't have any current. So there'll be a reverse voltage on those diodes that will make them behave like switches that are turned off. So these here will be disconnected from the circuit. And then if the microcontroller wants to change frequencies, it'll know to switch to whatever the appropriate filter is, and it'll turn on the other transistor, and then you'll use the other filter or the third filter like that. So any questions about that?
Is this a stable effect? So when you start a transmission, does the microcontroller set this up once and then?
Yeah, so for the
Normally
entire
see-
time that you're transmitting, it'll keep this MOSFET on, and it'll keep that filter active. So what it does in the code for the microcontroller, actually this is something that I believe you're able to edit. If you go in and you can edit the code, and it'll say if you're transmitting in a frequency between this lower limit and this upper limit, then activate this MOSFET. And then so you can actually, if you want, you can design your own filters here that are different from the ones that come with the kit, and then program the microcontroller with your own frequency ranges that match whatever the filter is you put in there. And actually that's something a few people were asking about. So you could even have a radio that, instead of just doing these limited ranges like 20 meters to 10 meters or 80 meters to 20 meters, you could have both 80 meters and 10 meters on the same radio by using an 80 meter filter and a 10 meter filter, and then program it accordingly. You do need to program it though, because otherwise it'll think that a different filter is there. So, but you may not be able to cover all the bands in between too. So you might have some missing bands that you just don't have a good enough filter that'll work, which either will block the signal from coming out, or it might allow harmonics to go out, which could cause interference. You have to be a bit careful. The default filters and programming is designed so you don't have to worry about any of that. So if you do tinker with it yourself, you do have to take that into your own hands to make sure you're not causing interference.
So in the receive mode, there's no bandpass filter?
Actually, it is used on the receive mode as well.
And where's the TR switch?
Oh yeah, so I'll get to that on the receive side. All right, so any questions on this before we talk about the receive?
Actually, can you go back to the first block diagram?
Actually, yeah, here. Oh yeah, so this is the chain. So we have that RF generator chip, then the power amplifier. I didn't mention the transmit receive because on transmit that's just completely bypassed. And then you have the low pass filters and then the antenna.
Sorry, I was meaning other block diagram. But anyway, so what we have at just before the MOSFET stage in the power amplifier are two digital signals that are 0 plus 5 or 0 plus 3 or whatever,
Yeah.
out of phase, right?
Right.
But then through the application of the MOSFETs in the power amplifier, then what we have is a current wave that is actually not 0 to plus, but it's actually plus to minus. It's a
Right. Yeah.
So it's push-pull.
Yeah, it's a symmetric push-pull signal.
Okay, got it.
Okay, so yeah, so that's what happens when you are transmitting. So then when you're receiving, the signal takes a different path. So it first goes through the bandpass filter. So so it switches in the appropriate bandpass filter for the signal you're trying to receive. And why would you want to do that on receive? So on transmit, we wanted to filter out the harmonics because the power amplifier is generating a square wave, and we only wanted our fundamental frequency to go out. But on receive, presumably there's just going to be one frequency you're receiving, so why do you need to have a low-pass filter?
Because people are transmitting at all sorts of frequencies.
Yeah, so it's not just the signal that you want to hear, but there's going to be other signals too. And you do want to make sure that other extraneous signals don't get into the get mixed in, because they could actually cause you to not be able to hear the signal you're interested in if the signal power is too high. So that's what this first stage does. And then the next stage after it is this transmit-receive switch, which is just a Moffatt switch. So this one isn't a pin diode. It could be, but the advantage of the Moffatt is you just need a voltage to turn it on. You don't need to supply a continuous current like a pin diode, and that means you don't need to draw current from your power supply. So that saves a bit of power if you can use the Moffatt. And on the receive, the signals are weak enough that your source of your MOSFET here goes to ground through an inductor. So that means that the DC voltage is going to be ground. There will be some RF voltage that comes through here, and it'll act. So when you turn it on, it'll act like a switch, like this. So you'll have an RF voltage here, which you get over here. So this source won't be exactly ground. It'll oscillate with your RF signal, but it's going to be a very weak signal, so it's still going to be close to ground. So that's why you can use a MOSFET here, and you don't need the pin diode, compared to the power amplifier, where you do have a very high voltage, and you need the pin diode there. So the purpose of this switch is when you're transmitting, this will be open, and it'll prevent your very high power signal from getting into your receiver. So it protects all those components from those high voltages when you're transmitting. And then when you're receiving, this switch will close, and then the signal from your antenna can go into your receiver circuit. And then before you get to your receiver, though, it has this chip which acts like a switched bandpass filter. So first you have a low-pass filter, then it's followed by something called a bandpass filter. So that, instead of cutting off frequencies above a certain limit, has both an upper and a lower limit, and just looks for frequencies within a certain window. And this sort of looks complicated, but actually the inside of this chip, actually it just behaves like two switches with one pole and then 4 different positions that the switch can switch to. And both of these are switched together by this digital control input. So you have a 2-bit input, which gives you 4 different options, and using that from the signal from the microcontroller, you can tell these 2 to switch to any of those 4 different positions. And what it does is it lets you choose 4 different capacitors and 4 different tap points on an inductor. And that lets you change the inductance and change the capacitance, and that combination sets the center frequency of your bandpass filter. So you can center that bandpass filter on each of the different bands that you want to receive. And so in this position, for example, your signal would follow a path like this. The signal would come in and pass through this capacitor, and then through the switch, and then to that output, and then it goes back to one side of this tapped inductor, and here it goes through the full inductance, and it comes through this second switch, and then comes out. So any questions about that? So then once your signal is sufficiently filtered, then it goes to this chip here. Actually, this is the same chip as before, and this one is this one has those multiple switches that 1 to 4 position switches that are controlled by a signal coming in here, and the difference of how this is being used here is your RF signal coming from your antenna through all the filters goes into this transformer. I don't know if you may not have gotten to this step yet. Did anyone get to this step where you wind the 3 wires together? You twist 3 wires together? So okay, that's later on in the construction steps, but the purpose of that is to make this transformer that takes your input signal and produces 2 signals that are inverses of each other. So this transformer, all 3 of these coils are wound together on the same core, which means they all have to share the same voltage. So whatever voltage you have here coming from your input signal also appears here and here. And this center point here is so it's an RF ground, so that point is not going to be changing with the RF signal. It will be a constant voltage. So that means that the signal up here is going to be whatever this constant is plus your RF signal, and down here, the voltage here is going to be that constant voltage minus your RF signal. So those two voltages will oscillate in opposite directions like that. And then those go into the these inputs, which are then switched to these multiple outputs, and some of them are connected together to these capacitors here. And the way that those switches are operated is there's those two inputs here, which instead of coming from the microcontroller, those come from that signal generator chip. So that chip has 3 outputs. 2 of them, clock 0 and clock 1, come in here. And those 2 square waves that go in there are actually shifted with respect to each other. So the signals look like this down here. So they're shifted so that the rising edge of one of the square waves is right in the middle of the high portion of the other one. This is called a 90-degree phase shift. And what this does is, if you think of these square waves as being either a 0 or a 1, there's 4 different parts of this period. So you start out with 0, 1, then in the second part it's 1, 1, then 1, 0, then 0, 0. That's all the possible 4 combinations of 0 and 1. So that means using these 2 square waves, you can cycle through all 4 positions of the switch and then wrap back around and start again. So this circuit looks sort of complicated, but there's a way that you can rearrange it to sort of understand better what's going on. And so that's oh yeah, so that shows where the switches are that I was talking about. So this will cycle through these 4 positions, and so if you take this, you can rearrange it to look like this. So this is basically a sort of a mechanical analog of what's happening inside of that switching chip. So instead of using switches, in this mechanical analog, you can imagine that you have a sliding contact here that's touching a this metal rail, and then as it rotates around, it contacts all 4 rails one after another. So that's like those switches that switches from one to 4 different options and cycles through them and comes back. And so this would represent one of those switches, and then this side represents the other one. And if you trace through the wiring, you can see that they're connected in ways that they're always connected to opposite sides of these 4 different options. So this, if you imagine these sliding contacts just sort of rotating around, that's actually an equivalent of what that chip is doing. And then in the center here, you have that signal source. So that signal source in the center would be effectively the difference between these 2 sides here. So you have a positive voltage on one side and a negative voltage on the other, and then they oscillate opposite to each other. So that symmetric signal source you could imagine being here in the middle, but these are those 2 opposing voltages. So you have positive on one side, negative on the other, and always opposite each other. And then these resistors just represent the internal resistance of those switches, which is about 4 ohms. And then those are connected to some capacitors here on the output. And so they're labeled 0 degrees, 90, 180, and 270, which is their position around this circle. So so you have an interesting effect here. If you have a AC signal here, it's going to be continually changing as it's contacting this electrode, and then it'll contact this electrode here, and then this one, and then this one. So that voltage difference between these 2 is changing, and it's also changing what it's connected to at the same time. So if you start out with this voltage at its peak, let's say positive on this side and negative on that side, when this is right at the top center, then you'll have a positive voltage coming from this signal source going to that capacitor, and then a negative voltage on this capacitor here. And now if you were to exactly match the frequency of the signal source to the rotation frequency of the switch, then what would happen once this rotated 180 degrees? So if it rotates, so 360 degrees would be one full rotation of the switch. And let's say that that matches the same period as the one cycle of this of the sine wave. So, well, let's first say what happens after one full rotation if they are exactly the same frequency. If this starts out with a positive voltage here and goes all the way around and then comes back, at what point are you in that sine wave?
Same point.
Yeah, same points. You're back at the peak of the sine waves. You're at the positive peak, and so you'll have a positive voltage applied again to this electrode. What about halfway through the cycle, after half of the sine wave?
The opposite.
So yeah, so you go from the positive peak to the negative trough, and so, but if that matches the rotation frequency of the switch, where is that switch going to be at that point in the cycle?
Turned over as well. So
Again,
you're
it will be
So yeah, it'll rotate down to here. So if this starts out positive up here, and then by the time you get down here, if you go through exactly one half of a cycle, you'll be at the negative trough when it's down here. And so remember, you started out with a positive voltage here, creating a positive charge on that capacitor, and a negative voltage here, creating a negative charge there. So one half of a cycle later, this voltage has reversed, but you've also reversed the direction of the connections. So it's basically creating exactly the same charge on those capacitors as it did before. And this keeps happening.
Yeah.
So that means that an AC signal that you put in here gets turned into a DC signal across those
Where do you make
electrodes.
the measurement? Where are you measuring?
So all you have to do is just measure the voltage here. So this, you can, I'll get to that next, but there's an amplifier that measures this voltage. So
So you get a double,
yeah, so you have,
it's a rectifier.
well, it's not quite a rectifier because then there's these missing sections where it's connected to these electrodes. So you get, so this will just keep that, it'll hold that voltage when this slides off of that contact and goes to the next one. And then once it comes in contact again there, then it'll charge up those electrodes. So, but effectively what this is doing is it's taking your RF signal and turning it into a DC signal. And so if you were to shift the phase of your RF signal, then what would happen to these voltages here? Let's say if you were to delay your RF signal by 90 degrees, or about 1/4 of a cycle. So if so let's say your peak of your voltage, instead of happening when this was at the top, it was delayed by 1/4 of the cycle. Then what would happen to these voltages?
will be 0.
So yeah, so this would be 0 volts because you'd be passing through 0 as you're sliding here, and the same on the bottom. What about
The east-west one would give you a signal.
yeah, so your
north-south
signal would
is no
show up
signal.
across these instead.
Yeah.
So this system, it lets you not just measure the RF signal, but also the phase too. So if you shift the phase, then actually you'll change where this voltage appears on these different electrodes. And so what if you had a different frequency? What if the frequencies were mismatched by just a little bit? What's that?
You get a signal of the difference of frequency.
So yeah, so what would happen is if you have two signals with a slightly different frequency, that means that one way to think of that is having two signals with a phase that's continually shifting. So they would start out in phase, and if one was a little bit slower than the other, it would start to drift and happen either a little bit earlier or a little bit later. And they would drift out of phase until you go through one full cycle, and then they'd be in phase again. So, so what that would do is it would change where the position of these voltages are. So if they start out in phase, you'd have positive voltage here, negative here, and 0, 0. Then as they drift 90 degrees out of phase, you'd have positive here, negative there, and 0, 0. And it would go through a cycle like that. So, So actually, I brought a, to explain this a little bit better, I brought a mechanical analog here. So I have this stroboscopes, which will flash at a certain rate, and also a fan. So this is going to rotate at a constant rate. So if you were to match those two frequencies, then that's going to be analogous to this rotating switch. So by the way, is anyone sensitive to flashing? So if so, maybe close your eyes for this demo. So this fan is rotating at a frequency of about 25.4 hertz. So if I have a light that flashes at the same frequency, then I can make it look like it stopped. So you see that?
Maybe obscuring the camera.
So maybe let me come on the other side. Can everybody see it? So I have to just match them. There we go. So what this means is the fan makes one full revolution. So the light flashes, it makes one full revolution, it comes back to the same position, and it flashes again. So you could think of the flashing is analogous to the RF signal that's being input there. And then that flash will then occur at a certain point, and then you could think of it as adding charge to that electrode. And then where it is around that circle will determine where that positive voltage goes around those 4 electrodes. So now, if you look at here, the frequency is 20. Actually, would you mind dimming the lights? It might be easier to see if the lights dimmed a bit. Okay, yeah, that's good. Okay, so you see it looks like it stopped. That's 24.9 hertz. So now if I change this frequency a little bit, let's say if I go up to 25.1 hertz. So you see it looks like it's rotating backwards. So that's because this frequency is higher, so that means that the period is shorter between the flashes. So the fan doesn't have enough time to make it all the way back to the same position before it flashes again. So it's a little bit behind where it was before. So that's why it looks like it's moving backwards. And if I lower the frequency, then you see now it looks like it's moving forward. So if this frequency is lower than that one, then you get the fan can actually move a little bit past the same position before it flashes again. So so the same thing is happening here with the RF voltage. So if this is your signal that's coming in from the antenna, and this is your rotating switch, then the position of that, switch at the time when you get the peak voltage is going to determine where around that circle your positive voltage is going to be. And if you have a difference in frequencies like that, it's going to circulate around. And actually the frequency of that parent motion of the fan right now is equal to the difference in these two frequencies. So if you had a 1 hertz difference, let's go back to stopped. So it stopped at 20, okay, it's just about 25 hertz right now. So if I go up to, let's say 25 and a half, so it should go 1.6 so about 2 seconds to go all the way around. So that's half a hertz frequency. So the difference in the frequencies of your flashes and the rotation will determine the parent frequency of this of the fan, and it will also determine the frequency of that with which that voltage circulates around there. So by measuring those frequencies on the north, south, and east, west electrodes, you can then measure the circulation, and you can also measure the direction too. So you know if the frequency you're receiving is above your clock frequency or below your clock frequency, and by how much. So that, and the nice thing about those frequencies is those can be very small. So like this fan is rotating at 25 hertz, and you can easily measure a fraction of a hertz difference in frequency based on the slow drift of the image of the fan. And the same thing happens with these RF signals. So they're going to be in the megahertz range. You can have differences in the kilohertz, and so you can measure very fine differences between frequencies, which is exactly what you need for measuring a frequency shift keying signal, because these frequencies are only going to be differing by maybe a few hertz or so, and that's going to encode all of your data. So you need to measure these very fine differences and changes in frequency, and this is a really nice way to do it. And so now everything after this point, you don't need high-speed chips or things that can amplify very high-frequency signals. All you need is just audio frequency components, and that's enough to measure the signals past this point. So any questions about that?
Could also flash and half the frequency.
Oh yeah, so I think if I go down, yeah, so if I do half the frequency, then it'll make 2 full revolutions. So that's also another reason why you want to filter out other, yeah, here we go. So this is half the frequency, and you see it stop. This is why another reason you want to filter out other frequencies from getting into your quadrature sampling detector, because they can also produce this effect as well, even if they're not exactly on the frequency. Like you see half the frequency will do it too. So you want to make sure that that's filtered out, because otherwise you might see a signal that is not really there. It's actually a different part of the radio spectrum that you're measuring. So that's a good point.
Sort of a form of aliasing in a way.
Yeah. Mm-hmm. All right, any other questions? Okay, so we can turn the lights back on. So, yeah, so I mentioned everything after this point is an audio frequency. So you have these 2 channels. So you have this is you can think of as being a differential channel. So if you have a positive voltage here, you have the opposite negative voltage here, and vice versa. And the same with these. So really, there's only 2 independent channels with the differential signal on each side. So so that is amplified by this part of the circuit, which is a differential audio amplifier. I think all these parts are actually already on your board. So these are all surface mount parts. These aren't things that you're actually building. But this just takes in your signal, and it multiplies the voltage by about a factor of 10. And it also does some filtering, so it only passes this audio part of these audio frequencies between about 10 and 30 kilohertz, and it makes sure everything beyond that is filtered, because otherwise that could cause problems when you try to digitize it, which is the next step. So then your amplified audio signal goes into this chip here, which is a 24-bit analog to digital converter. So it has all these different discrete voltage levels, and it measures your audio signal, and then it finds the level that's closest to that analog voltage, and it samples it at 48 kilohertz, so 48,000 times per second. It'll try to measure which level is closest to your signal, and that level is encoded by some 24-bit binary number. So it's actually that's a lot of levels. That's 2 to the 24 levels, which actually so 2 to the 24 is 16 million levels. So so that's very, very fine-grained measurement of your signal. And then once it's digitized, this is sort of a rough depiction of what your digitized signal looks like. It looks like it has discrete time samples and voltage levels. And this is what then gets sent through this data bus back to your microcontroller. And your microcontroller does a little bit more processing on that. And then that's sent through USB back to your computer. And it acts just like a USB sound card. So so your computer knows how to deal with USB sound card and take in digital audio samples. So that's how the signal is treated after that. So does anyone know why you would use that many bits in your audio sampling, or your analog to digital converter? Why use so many bits? Because that's creating millions of different voltage levels. Why do you need that many levels? Can't you just get close enough and measure this sine wave?
Extra dynamic range in the RF?
So, yes, exactly. So has anyone not heard of the term dynamic range? Raise your hand. So dynamic range means the ratio of the biggest signal that you can receive to the smallest signal that you can receive. So the smallest signal will actually be limited by multiple things. One of them could be the step size between these voltage levels. So if you had a sine wave that was too small, that it doesn't cross these levels, you're actually not going to be able to measure it at all when you digitize it. And so if you don't have enough of your voltage levels, you're not going to be able to even see these very weak signals. You'll only be able to see the strong ones. And you could amplify your signal to see the weak ones, but then the biggest signal will go beyond the range of your analog to digital converter, and instead it'll be what's called clipped. It'll go beyond the maximum voltage, and it'll just saturate at 1111111 and so on. And so in order to be able to measure both strong signals and weak signals at the same time, that's why you need so many different voltage levels. And I think this one, it has so many bits that it's not limited by the discrete size of the voltage levels. It's limited just by the noise in the circuit. So there's going to be a continual noise added to the signal, and it's digitizing that as well. And then the weakest signal will be determined by the signal that is just above that noise level to be big enough to be detectable. And so the nice thing is, by using so many bits, you make sure it's not your analog to digital converter that's limiting that minimum signal strength you can receive. So, all right, so I think that concludes the overview of the circuit and what's going on. So there's a lot more you can discuss in each of these different parts of the circuit. But I mentioned the different filters. So here's the default components that come, or the default option for the 80 to 20 meter version. So if you want to do the 10 to 20 meter option, we do have the new capacitor values. So if you look in the manual, it says use this capacitor and so on if you're doing the 20 to 10 meter option. And it also talks about winding the toroids as well. But they didn't have that option when we ordered the kits, so they just added that new option. But you needed to get a different core material in order to wind those toroids. So you can use the core material that we have for the 80 to 20 meter option and just change the number of turns in order to use it for the 20 to 10 meter option. So if you're doing that, then don't follow the instructions when you're winding the toroid. If you're doing the 20 to 10 meter option, so don't do those instructions in the manual when it says number of turns. Instead, follow this here, because those instructions are for a different core material. So we're just going to reuse the same cores that were intended for the 80 to 20 meter option. We're going to modify them to work with the 20 to 10. And these are going to be the number of turns that you'll use, which I calculated should get pretty close to the right inductance values. And we have some VNAs here, so we can do some fine tuning and measure those to make sure that the inductance values are right. So those are on one of the early pages in the manual. And also this one here, these are the tap points. So this is that tapped inductor, which is part of that bandpass filter. So any questions about that? So I'll leave this up once we get back to building. And also just for people who are new this week, so as I already mentioned, the 80 meter versus 20 meter option. Also, if this is your first week, be careful when you get to different points. It'll mention a 9 volt and 12 volt options. That's when you're winding that transformer that looks like binoculars. And make sure you follow the 12 volt option, because we have a 12 volt power supply. Otherwise, if you use the 9 volt option, 12 volts could overpower it. And also try to break up into groups. Make sure that at least one person in each pair at each soldering station has some soldering experience before. And also make sure you check your components before soldering. And also when you get to the steps with the enameled wire, ask someone with experience to make sure that that's done properly. And also for people who weren't here last week, make sure that you, each station you have a soldering iron, solder, circuit board holder, safety glasses, and the assembly manual. If you need safety glasses, they're over there by the sink. And also, if you're getting ready to test your circuit, make sure if you're not very well experienced with circuits, or if you're sort of new to this, make sure you just ask someone with experience to do a visual inspection before you turn anything on. There could be some solder blobs that might be shorting something, and if you turn it on, it could blow some component up. So it's good to catch that before you apply power. Much easier to correct. And also, we reviewed this last week, but for people who are new, so main safety concerns are burn hazards and eye hazards. So because you're going to be using the soldering iron, just be careful of things that get hot. The components and the board can get hot too, so careful touching those after you're soldering. And if you do burn yourself, there's a sink over there. You could use some cold water. And also eye hazards. So the solder can occasionally fly off the tip of the soldering iron if you flick it into something. So make sure that when you're soldering, or anyone who's near the board as you're soldering has safety glasses on. And also if you're using wire cutters, that could cause some things to fly too. So make sure that you're using safety glasses, and people around you are aware if you're going to be using wire cutters. You don't want something to fly into someone's eye. It's unlikely, but you just want to be careful. So any questions about that? No? Okay. So I also brought a QDX kit with an antenna that I can demo. So if you want to take a look at that demo before working on your kit, I'll be setting that up putting the wire up in a tree just outside of the Packard building. So if you want to see what the completed kit will look like, you can do that. And I also have, we can also talk about some of the accessories you can get with the kit, like a battery, end-fed half-wave, antenna tuner, and those sorts of things. Otherwise, if you just want to get started working on your kits, then you can get to it.